Okay, today we're going to continue on with our exponent notes. We're going to talk about the next three rules. Actually, we'll do three of them here. Let's take more of those dogs. We're going to talk about the zero exponent rule, the product rule, and the quotient rule today. So let's start with the easiest one. That is the zero exponent rule. So here's what the zero exponent rule means. It's nice and simple. Any number to the zero power equals 1. So x to the zero power equals 1. That means that 4 to the zero power is 1, a to the zero power is 1, 1983 to the zero power is 1, and negative 2 to the zero power is 1. Anything to the zero power equals 1. That was a pretty easy one, huh? Because you're just taking that number, multiplying it by itself, zero number of times, but you still have that first number that you would have multiplied, right? Okay, now let's talk about the product rule. You can see right here that we have 2 to the fourth power times 2 to the third power. The first one, 2 to the fourth power, is like 2 times 2 times 2 times 2. And then the second one, 2 to the third power, is like 2 times 2 times 2. All together, how many 2's do we have? 7. So 2 to the fourth power times 2 to the third power is 2 to the seventh power. The shortcut is called the product rule. If we have the same base and we're multiplying those two expressions, we can add the exponents and keep the base the same, keep it x or whatever number or variable the base is, and add the exponents together. We're still multiplying those two expressions, but the shortcut is to add the exponents. So when in doubt, you can always write it out like this and count up how many you have, but the shortcut will just make it a lot faster. Let's try these examples. So 4 to the fifth power times 4 to the sixth power, the shortcut would be to keep the base and just add the exponents, and that would be your answer, 4 to the 11th power. For example 2, a to the third times a to the fourth, we'd keep that base and add the exponents. All right, if you look at number 3, we have coefficients here. So we're going to multiply those coefficients together. 5 times 7 is 35. And then we're going to multiply the x's together because those have like bases. So we have x times x to the sixth. One thing to remember is if it doesn't have an exponent, it actually does have an exponent of 1. There's 1x right there and 6 x's next to the 7. So we're going to keep the base and add the exponents. 1 plus 6 is 7. If you look at the next example, we have coefficients that we can multiply. We have a 12, and then we don't actually have a coefficient on this one, but when there's not 1 written, it's really a 1. So 12 times 1 is going to give me 12. And then we're going to multiply the variables together. The variables are x to the third and x to the ninth. To multiply those, we keep the base and we add the exponents together. Beautiful. Let's keep doing that same idea here. Multiplying first the coefficients. 6 times negative 5 is negative 30 because a positive times a negative is always negative. And then we will multiply the variables. They're both a, so they have the same base, which means we keep the base and we just add the exponents. And the last example, I know I really like to change colors a lot, but we're going to do the coefficients. 10 times 3 is 30, and then we're going to do the variables, a squared times a cubed. We keep the variable the same, and we add the exponents. So that's how you use the product rule to simplify with exponents. I'm going to go back through and circle because, you know, I love to circle my answers. If I'm a student, I'm doing that so my teacher can find my answers quickly. All right, we're going to do one other rule today, and that is the quotient rule. The quotient rule, I bet you can even guess what it is if you're really thinking about this. So if we have 3 to the 7th power, that's 3 times 3 times 3 times 3 times 3 times 3 times 3, 7 of them. And in the denominator, we have 4 3s. And in math, we know that if we have a number divided by itself, it actually equals 1. So that means that 3 divided by 3 is 1, 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 canceling out those 4 pairs of 3's, leaving us with just 3 3's, which is like 3 times 3 times 3. That's probably not what I wanted to do. Now that I'm looking at the notes. Maybe we wanted to show it. I wrote them in the wrong places. We have 3 times 3 times 3 left right here, and that's 3 to the 3rd power. So if you're thinking about what the shortcut might be, when we have the same base and we're dividing, we subtracted the exponents. We kept the base the same and subtracted the exponents. And that's what they're showing you right here in this box. If we have the same base and we're dividing, we can subtract the exponents. We're still dividing, x to the a power and x to the b power, but the shortcut is to keep the base and subtract the exponents. So let's try some examples. Let's look at number 1. If we have 12 to the 10th power divided by 12 cubed, we can keep 12 the same and simply subtract the exponents. What happens when we have coefficients? Remember, we are dividing. So we can divide 18 by 3 to get 6, and then we can use the shortcut on the variables. W to the 7th power divided by W to the 6th power, we would keep the base the same and subtract the exponents. Now, of course, you don't have to have a 1 on there. I wouldn't mark it wrong, but 6 times W would be a better answer without the exponent of 1. All right, let's look at the next one. We're going to divide 4 and 16. Well, 4 divided by 16 is 1/4. So that's fine. If it doesn't divide, if the denominator doesn't go into the numerator an even number of times, just treat it like a fraction. You can make it 1/4. And then you have more than one variable in this example, but that's okay. Remember, they have to have the same base for you to use that shortcut. So we'll use the x's first. X to the 8th power divided by x to the 5th power is x to the 3rd power. We're subtracting 8 and 5 to get the 3. And then we have another pair of exponents here. Variables here. We have y's. We have y squared over y squared. Now, anything divided by itself in math is just equal to 1. But the shortcut is to subtract 2 is 0. So if we had y to the 0 power, we know that that is also 1. So that's 2 ways of proving that y to the 0 power, or y squared over y squared, is 1. So let's simplify my answer here. I don't have to write a coefficient of 1, so I'm going to take that off. I don't have to write times 1 on the end of anything, so I'm going to take off the y. So this is my best, most simplified answer would be y cubed over 4. All right, moving right along here. Let me switch to yellow. 28 divided by 12. Well, 12 doesn't go into 28 evenly, but we can simplify that. Remember, treat it like a fraction. If I divide 28 and 12 by 4, I get 7 over, whoops, wanted me to do straight lines, over 3, because 28 divided by 4 is 7 and 12 divided by 4 is 3, and then I can deal with that variable part. So I have an x in the numerator and an x in the denominator. I'm going to subtract the exponents to get a 6. So these would be my final answers. I'm going to circle my answers to make my notes nice and neat. All right, I'll see you guys next time when we finish up this page of notes. Thanks for watching.